And if anybody else would like to come up on stage, I always invite anybody who'd like to hang out. If you feel free to raise your hands. Somebody will bring you up. If not me, hopefully. If I say something that you have a question about, it's usually better to be on stage and ask it than to put it in the chat. But you can also do that if you'd like. And with that, let's go ahead and get started. I want to talk about black body radiation today. It kind of came to me in a flash that this is a nice topic. We're not going to get very deep into it. In fact, there could be, it's conceivable that we'll have a second week on this because are more things to say about it. But I don't think we'll say them in this sequence. I just wanted to kind of touch on the idea of black body radiation here. You've probably heard the term before. If you go to slide 2, what is it? It's black body radiation is the electromagnetic spectrum, the radiation that is emitted by a perfectly black, meaning absorbing, an object that absorbs all light that falls on it. Right? A black object is an object that technically doesn't reflect anything, doesn't reflect light of any frequency. And in specifically, it should be in thermal equilibrium with its surroundings. I'm not going to dwell on that, and in many cases, that's not actually very important, but it is technically necessary for the definition of a black body. You're familiar with black body radiation because when you sit in front of a fire, the fire heats up the air a little bit. The house will get warmer, especially if it's a cabin. You have a big fire, you've got a nice heat exchanger and all of that. But for most people with crappy fireplaces that don't do a very good job of heat exchanging, your best bet is to sit in front of that fire and not so much feel the warm air as just literally feel the radiation, electromagnetic radiation produced by the hot surroundings of the fireplace, by the fire and the logs and the fireplace itself, radiating, hitting your body, being absorbed by your body and warming it. That's radiative heating. You do the same thing with a space heater. When you sit in front of that glowing element, you feel that radiation. And indeed, the red color of the fire, the red color of the element in a space heater reflects the fact that it's, maybe at 1,000 degrees Kelvin or maybe as much as 2,000. I don't know. I don't know how hot a space heater gets. It's hard to make things 2,000 Kelvin without them melting. But when you get something up to hundreds and hundreds, even 500 degrees, well, 500 degrees Kelvin isn't too much, but even that you will feel. Anything above room temperature, which is about 300 Kelvin, you'll feel the radiation from that. And this slide gives you a kind of an introduction to what it looks like. If you look at the graph first, there are curves there reflecting the black body spectrum of objects at different temperatures. It's notable, number one, that the spectrum in detail depends only on the temperature of the object. That's the only thing that matters. When we talk about the spectral, this is the spectral radiance. It is the amount of power emitted per unit surface area. We'll talk about this a little more. Per unit surface area, per unit solid angle, as it's called, the angle outward from that surface area, the amount of well, how do I want to say that? We've talked about solid angle in previous bites of physics. Just basically kind of asks how much are you willing to wrap around that surface to gather the area. Maybe I've already said too much. Per unit area, per unit solid angle, and per unit wavelength. So this is the amount of power emitted over a slight little range of wavelengths from a small area into a small solid angle. It's enough for our purposes, really, just to understand that this is kind of just the radiant power, that it depends on the temperature in this particular way. And you'll notice that it depends in a very strong way on the temperature. There's a 3,000 Kelvin curve there, a 4,000 Kelvin curve there, and a 5,000 Kelvin curve. And you can see the enormous difference between an object at 5,000 Kelvin and one at 3,000 Kelvin. They don't show an object at room temperature, 300 Kelvin on here, because you wouldn't see it. A 300 Kelvin curve wouldn't rise up above the zero line that you see there. In fact, I was reading, I think in this Wikipedia article, it was pointing out that at room temperature, you notice this has the visible spectrum in there. That's the range of wavelengths that actually constitutes the visible spectrum. At room temperature, a black body will emit a 1 square meter area of a black body at room temperature will emit one visible photon in a little less than a minute. So every minute it emits one visible photon. We haven't talked about photons yet, but that's kind of how weak the intensity gets. By the time you raise something to 3,000 Kelvin, it's radiating a fairly significant amount of power in the long wavelength end of the visible spectrum. That's the red end of the spectrum. But it peaks, you'll notice, a little above the visible spectrum at a wavelength of about 1 micron, something like that. That's in the near infrared. We don't see 1 micron wavelength, and it's in the infrared region. That's why you feel that. All of that radiation in the infrared is what you're feeling when you sit in front of a hot object. A 3,000 Kelvin object is going to be glowing very strongly in the red because it emits a fair amount of large wavelength visible spectrum. And as it rises to 4,000 Kelvin, it will start to get kind of yellowish a little. It's emitting now a fair amount of blue light, green light, yellow light, orange light. It'll still look mostly red, right? It's down there in the reddish end, but it's now starting to emit light at all wavelengths in the visible spectrum. And by the time you get to 5,000 Kelvin now, you're actually peaking kind of in the yellow region. Beyond 5,000 Kelvin, at some point, not too far beyond 5,000 Kelvin, the black body radiation will peak at wavelengths that are shorter than visible. That's in the ultraviolet. So it'll be putting out most of its energy in the ultraviolet and just having a tail that creates mostly blue light. And such an objects that are at temperatures of 6, 7,000, 10,000 degrees will look bright blue, bright white, kind of a bluish white. You know that an object like that, like a star that shines with bright bluish white light, is a very hot star, for instance. Okay, so I put a couple of things there. There's two things that were known about this by the late 1800s, and one is that the peak of that spectrum is inversely proportional to the temperature. When you reduce the temperature by a factor of 2, you increase the wavelength of the peak by a factor of 2. And so that's called Wien's displacement law, and there was just a constant there, which is just the proportionality constant between the wavelength of the peak and the inverse temperature of that black body. So that was one thing that was known, was that was true. Another thing that was known is that the total radiant power is, as we've already talked about, strongly dependent on the temperature. An object, it increases as the fourth power of the temperature, so that when I double the temperature of an object, it emits 16 times as much power as it did before. And that's reflected in the fact that 3,000 Kelvin that spectrum is so much lower. This, what we're talking about now, is what's called the integrated power. You take the area under that curve, and that's going to give you something that's proportional to the fourth power of the temperature. By the time when you go from 3,000 to 5,000, you haven't even doubled the temperature, but you can see that the area is certainly at least 10 times as great there, and that probably is something like 10 times as great. And there's a constant called the Stefan Boltzmann constant. That's just an observational constant from the data. These everything that we're saying here really just kind of reflects observations. There was no theory for this, but there were these observations of black body radiation. They weren't very accurate by the end of the 1800s, so this reflects kind of our modern understanding of those things, but they at least understood the idea of Wien's displacement law and the fourth power dependence of the power. That those are things that they did understand. So I'm going to stop there for a second. Any comments, questions on what we've talked about so far?
I was wondering, these curves that we see on the slide, this implies that, so first question is, does it apply to all bodies? So all materials are the same, they glow at the same rate. And
Right.
does this imply that whenever you heat a body, it will emit all sorts of light, but then the peak of it will be somewhere?
That. What did you say? The last thing, when you what a body?
So if you heat, let's say you're
Oh, oh,
heating this
yeah.
piece of metal, and so it's emitting all sorts of radiation, but then the bulk of it kind of moves towards the more energetic radiation, so towards the blue, the hotter it gets, but it keeps emitting all sorts of other lights as well.
Yeah, that's right. So there's a lot of things. We'll get more into some of those questions on the next slide. We are talking here, and it's really important. I should have emphasized more. We're talking here about a perfectly black object. An object, interestingly enough, this is the emission coming from a body that is a perfect absorber of light. And you might wonder why I'm talking about the emission of such a body if the thing that characterizes it is the fact that it absorbs all light. We'll get to that on the very next slide, why those two things are very closely related, in fact, identical in the case that we're talking about here. And yes, when you heat an object, as you heat an object, this black body radiation, the spectrum does move toward the blue, move toward higher wavelengths. At first, I thought you said when you eat a body. That's why I was a little confused at first. I thought you were making a joke.
You can think about it, because like these temperatures are quite hot, like 3,000, 5,000 Kelvin. This is quite hot. You can't imagine anything in our like day-to-day lives except fire itself, probably. I can't imagine water vapor under that temperature. It'd be so hot.
Yeah, that's right. 3,000 isn't white hot. 3,000 is still red hot, but it's getting that's getting close to being something more than red hot, as you can kind of see in the diagram there. But you're right. We see these temperatures in stars. These are typical temperatures for stars: 3,000, 4,000, 5,000, 6,000. I don't think usually 7,000. Maybe so. Certainly not more than 10,000, I think, typically for stars. So these are the temperatures that we see there. And amazingly enough, stars are, to a pretty good approximation, black bodies. So I want to get into what that means, how we can call something that is emitting so much radiation a black body. And before we go on to slide 3, one thing I didn't mention was the classical theory line. We're going to get back to that. That's not a black body line. This is when we applied classical thermodynamics to the problem of a black body. That's what we got for 5,000 K. If you wanted to calculate what classical theory said the spectrum of a black body at 5,000 K is, that black line over there is what you get. And you can see it's wildly wrong. And that's what we want to get at, is what's the cure for that classical theory. So in slide 3, I'm going to talk about what's called cavity radiation, because this is the way physicists approached the theoretical question of black body radiation in the late 1800s. They considered, they asked themselves, what would, because they knew that hot objects radiated electromagnetic energy. So the question is, okay, if you were inside a cavity, so you didn't have the thing interacting with anything other than itself, right? The light in the electromagnetic radiation emitted by the object could only be absorbed and re-emitted, etc., by the object itself. And so if you held that object at a constant temperature, the electromagnetic radiation in that cavity could reflect only the temperature of the object and maybe the material, maybe the kind of material it is. There were other possibilities. Turns out, and we know now, that the radiation in such a cavity does depend only on the temperature of the object itself. And that's what they were looking at. They wanted to eliminate the confounding influences of reflections, of interacting with other objects in the environment at different temperatures. So you just consider the energy within that cavity. Now, if you take such a cavity and you drill a little hole in the wall, what does that change? Well, it doesn't change very much. And in fact, what does it do? Any light that comes in through that hole is going to bounce around if it's reflected at all. If the surface inside isn't perfectly absorbing itself, it's still presumably going to kind of reflect off that surface. It's unlikely to bounce right back out of the hole. So that radiation, any radiation that comes in that hole is going to bounce around. It's going to get absorbed a little bit, a little more absorbed, a little more. Pretty soon, any incident radiation will end up having all of its energy absorbed by the object, helping, maybe changing the temperature if you want. But as long as we don't have anything but a small hole, one would expect pretty quickly that the amount of radiation coming in through that hole is kind of balanced by an amount of radiation that comes out of that hole. And the amount of radiation coming out of that hole reflects the thermal radiation in the cavity, because overwhelmingly anything coming in is absorbed. Ultimately, anything coming out is simply part of the radiation field that would have been in that cavity, whether or not there was a hole. And so you ask yourselves, so you can basically create a black body this way. And in fact, one of the best ways to make a black body is to take a stack of old-fashioned razor blades, put them right together. So the sharp ends are all kind of close together, but because they're sharp, there's a little space. Light coming into a stack of razor blades will reflect around and around. And even though the razor blades themselves may be pretty reflective, ultimately anything coming in gets pretty much absorbed. And what comes out of those razor blades is going to be the thermal radiation reflective that is characteristic of the temperature of the razor blades. And since that is room temperature, typically, it means it's going to be pretty black. If you make a stack of razor blades like that and look at it edge on, you'll be surprised how black it is, how little light you see coming from it, even though they're all made of steel, right, which is presumably pretty reflective. So that's the kind of that's what people did to look at the thermal radiation, and they applied classical thermodynamics along with what's called statistical mechanics, looking at all of the radiant modes of oscillation within that cavity and determining how much energy there should be at different frequencies at different wavelengths. Before we go on here, I just want to mention this one thing. So I've kind of showed you, I think, in a way, well, I haven't actually explained this. So there are these concepts of emissivity, how emissive an object is, and how absorptive it is. I think it should be pretty obvious that a perfectly black object should have an absorptivity of 1, the highest on the scale. But it also turns out that if you impose thermal equilibrium on whatever system it is you're looking at, there's a concept called detail balance that says that any energy in any given wavelength range, if the object is absorbing a certain amount of radiation at that wavelength, it has to be emitting that same amount of radiation. So an object that is under the black body conditions that the object is operating at thermal equilibrium, the absorptivity of an object is equal to its emissivity. A black object emits much more. Well, a black object emits just as much, just as well as it absorbs. It has an emissivity of 1 because it has an absorptivity of 1. And I think we all kind of know this intuitively. If you wear black clothing out in the sunlight, it's hotter than white clothing because white clothing will reflect sunlight. You don't get as hot in it. Black clothing will absorb the sunlight and you do get hotter. But going right along with that is the fact that if you stand next to somebody wearing black clothing, you will receive radiant energy from that object beyond just the reflected sunlight that reflects off of it. You'll in some sense be able to feel the warmth. If you put maybe a better way to say it would be that if you put a perfectly white object at 1,000 degrees right next to you, you actually wouldn't feel any radiation, any thermal radiation, because a perfectly white object has an emissivity of 0. It emits no thermal radiation for the same reason that it absorbs no thermal radiation. Now there is no such thing as a perfectly white object, so you'll probably never experience that. But that's an odd. You will of course get the reflected light, but you won't get any light that comes from, or any electromagnetic radiation that comes from its own temperature. You won't be able to feel its temperature. Okay, let me stop there again. Any comments, questions? What's going on?
So let's say we have, I don't know, I'm imagining like more day-to-day examples. So if you have, let's say, a white plate, and if you have a black plate and you put both in the microwave or in the fire, because that white one, assumingly reflects more, so it has an absorptivity of less, as a lesser absorptivity. I mean, so it will take longer to heat. Is this good understanding?
Yeah, it's good theoretical understanding. The problem is that when we talk about a perfectly black object, we really mean an object that's black not only to visual, not only
Oh, so
to in the
all sorts
visual
of
range,
electromagnetic
but
radiation.
overall,
Yeah.
that's right, over all wavelengths. And the same thing with white. It's a rare object that will perfectly reflect electromagnetic radiation of all wavelengths. And so this is all kind of an idealization. Yeah. Okay. Oh, and I didn't mention albedo. Albedo is a completely separate thing. How reflective an object is. Obviously, if an object is reflective, it will not necessarily to the extent that it's reflective, it won't be absorbing light. But on the other hand, one can also have transparent media. So albedo doesn't take into account the fact that you can fail to absorb while also failing to reflect. So there is that, and it also has to do with, and all these things, of course, are kind of wavelength dependent. Usually, when we talk about the albedo of the moon, for instance, the moon has an albedo of about zero point 0.1 something, I think, meaning it reflects about 10% of the light that falls on it. So that we see the moon due to reflected light of the sun. The moon also radiates light radiates electromagnetic radiation anyway, but because it's pretty cold, of course, we don't see it in its black body radiation. We see it due to its reflectivity. And those are two things that operate kind of in different ranges of the different wavelength ranges. Okay, let's move on to slide 4 now, when we talk about that classical. How did that classical theory work? When we apply that to cavity radiation, I kind of waved my hands about the idea that we actually do look. It's anybody has any more interest, you can go to that hyperphysics link there, and there's links to the detailed how we derived this classically, and it is kind of important for understanding the final resolution of black body radiation as well. But it really was literally taking the cavity and thinking about modes of oscillation, very much like modes of oscillation in a bathtub. When I was a kid, I remember I used to love to get in the bathtub and I would slosh my body back and forth. And when I did that at just the right frequency, I could get the waves building up, right? It'd go all the way to the front of the bathtub, to the back of the bathtub, and you can kind of get those waves going. And you find there's that has a very specific frequency. You can also, although it's harder to do, I see all the laughing faces, but come on, don't tell me you didn't do this too. I love doing that.
I'm laughing because I used to do it.
What you could, if you did that, you may have also at some point realized that you could kind of sit in the middle of the bathtub and use your hands kind of pushing water both ways so that it would slosh up on both ends and then come sloshing back into the middle, forming a peak, and then sloshing back to both ends and so on. You could also do that, but then you had to do that at a higher frequency. So that mode of oscillation is a higher frequency. And then there are other modes too that you could also slosh back and forth. If you slosh the water back and forth in the bathtub, you can do that. That's also a higher frequency than sloshing it from front to back. Sloshing it from side to side is a higher frequency. If you look at this in detail, you'll start seeing, wow, there's lots of different, you can have some that slosh from one corner to the other corner, and they can slosh in different frequencies from side to side while they're sloshing back and forth and from end to end. All sorts of modes of oscillation. And that's exactly what people did, looking at the modes of oscillation for electromagnetic radiation in the cavity. And when you do that, you find that the number of modes of oscillation increases, the density of these modes increases as you go to shorter and shorter wavelengths. You take shorter and shorter wavelengths, there's more and more ways that you can slosh electromagnetic radiation around in that cavity. And the classical thermodynamic assumption was that each one of those modes of oscillation would be populated with the same amount of energy. That's that's an argument from what's called statistical mechanics, that each mode should have the same amount of energy in it. And since there are more and more modes as you go to smaller and smaller wavelengths, you expect the amount of energy in the cavity to increase as the wavelength increases. And when you do this calculation, it's pretty simple, actually, once you kind of understand the whole mode counting thing. You end up getting this Rayleigh-Jeans law, which is written there, and it's a constant, 2 times the speed of light times a thing called Boltzmann's constant, which comes out of thermodynamics. Don't have to dwell on that, but its value is there. The important part is that you do get a radiant power that is directly proportional to the temperature and inversely proportional to the 4th power of the wavelength. And that's just reflecting the fact that you get more and more modes as the wavelength gets smaller. They increases the 4th power of the wavelength effectively. And that function is plotted there on the same graph as the black body radiation for 5,000 Kelvin. Now, as soon as we got that formula, we noticed two things. Number one, it does a really, really good job of giving us the black body radiation at really, really long wavelengths. If you look at that graph, you'll see that the dotted line and the solid black line look pretty much the same out there at very, very long wavelengths. And in fact, they really do. They are exactly the same, or they get more and more exactly the same as you go to larger wavelengths. So there's something right about this formula that it gets that exactly right without any adjustable constants. Speed of light is known. Boltzmann's constant is known. And so you get exactly the right thing. We haven't massaged this in any way, but it only works at really long wavelengths. The much worse thing about it is that as the wavelength gets shorter and shorter, it gets ridiculously out of whack with observation and obviously wrong because it literally predicts that an object at any temperature will emit arbitrarily large amounts of radiant power at short enough wavelengths. And that means that whatever energy content that object has, it's going to immediately radiate it away in short wavelength electromagnetic radiation, which means gamma rays, X-rays. Any object at any temperature at all will be a potent source of gamma radiation and X radiation for a moment until it cools literally to absolute zero, which is the only temperature it can be at and not radiate. So there was something wildly wrong about this classical approach, and everybody knew that. And the question was, what do we do about that? So I really want to just concentrate. I want to stop there for a moment. I only have, I think, a couple more slides and a kind of a conclusion in which we'll talk about that solution. Uh-oh, Andy swiped the wrong way. I saw him unmute, and then let's see. Let's get him back up on stage here in a moment. Or maybe he did. Maybe he didn't swipe the wrong way. Maybe he swiped the right way. Anyway, we'll bring him back if he comes back in. Any comments on that? Okay. Yeah, watch for Andy, everybody. And raise your hand if anybody wants to come up on stage and ask a question or comment. That would be great. I see it, Nancy. Thank you. Thank you for being brave enough to admit that you played in the bathtub, too. Okay, slide 5. So how do we fix this problem? So this is what happened in 1900. Max Planck was thinking about this problem. By the way, most of this was kind of only understood very shortly before that. The Rayleigh-Jeans law was obtained almost the same time. It created, there was obviously a push to figure out what was wrong with it. Max Planck introduced an ad hoc assumption. He could see that the problem was all of these modes of oscillation at high frequencies. And so what he did was he hypothesized that energy could only be added or subtracted to the electromagnetic field, essentially that these modes could only be populated with energies that came in chunks, with those chunks being proportional to the frequency, directly proportional to the frequency, and therefore inversely proportional to the wavelength. The smaller the wavelength is, the bigger the frequency. The bigger the frequency, the bigger the size of these chunks. And he just said, so let's just suppose that the energy is proportional to the frequency. He put a proportionality constant in there. He wasn't hypothesizing a value for that, but he said, let's just put a proportionality constant in there to get this result, to implement this hypothesis. And the idea of that was simply to say that then in classical thermodynamics, because you expect each mode to be populated with the same amount of energy, if that basic energy, which by the way is Boltzmann's constant times the temperature, Kb times T was kind of the basic amount of energy per mode, really a half Kb times T if you want to be picky about it. But Boltzmann's constant times the temperature gives you roughly the amount of energy per mode that you expect to get. But what this would do then would be that at very short wavelengths, at high frequencies, the chunks of energy themselves would be bigger than the amount of energy that you'd expect to see in that mode. And since that was the smallest chunk you could get, these modes simply would find themselves unpopulated, increasingly unpopulated as the frequency got bigger, as the wavelength got smaller. And so, in that way, he would limit, even though the modes existed, the high frequency, low wavelength modes wouldn't be populated with energy. And therefore, we get this fall off that we need at the short wavelength end of that spectrum. A completely ad hoc assumption. And he used that assumption and then once again used the statistical mechanics ideas to derive the formula that you see there for the radiation. And the amazing thing about that result is that by simply picking the right value for his proportionality constant, that function fit the experimental data perfectly as far as we could tell. We couldn't tell very well at the time. We didn't have very accurate measurements of black body radiation, but we had accurate enough ones to know that the Rayleigh-Jeans law fit pretty well at high wavelength, large wavelengths, and that obviously it was wrong at low. We knew there was a peak. We knew fundamentally what the shape looked like, and he found, I shouldn't say that he found, but he found a value close to what I'm saying here. We now know that that with a value of what's called now Planck's constant, H is called Planck's constant, with a value of 6.62, and it goes on to about 10 digits after that, times 10 to the minus 34th, 10 to the minus 34th joule seconds, he could get an apparently perfect fit to the observational data. And we now know that really is true. You get, as far as we can tell, you get a perfect fit to the spectrum of a black body using a value for Planck's constant, which we now know 10 or 15 decimal places. And so that was pretty amazing. There was something right about his assumption, and we'll get to that on the penultimate slide here. But I just wanted to also just say, just a little mathematical curiosity. It's a mathematical fact that e to the x is equal to, e is this base of the Neperian logarithms thing. You've seen that in mathematics before. It's a very special number that has lots of nice exponential properties. Turns out that e to the x is approximately equal to 1 plus x when x is really small. So that means if you look at that formula that I put up there, if I assume that exponent on e, that exponent for e is very small, then I can write it as follows. Rather than being e to the hc over lambda kbt minus 1, I can just write that as 1 plus hc over lambda kbt minus 1. And so the ones cancel. I'm left with just the hc over lambda kbt. And because it's 1 over that, I end up getting lambda kbt divided by hc, as long as the wavelength is large. Because if the wavelength is large, then the exponent on the e will be small, will be much less than 1. As long as I choose large enough wavelength, at some point, that exponent will be small. And when you put lambda kbt, when you multiply the thing in front in the expression for b, if you put that, if you substitute that approximation for the fraction at the end of the expression above, you end up getting exactly the Rayleigh-Jeans law. So the Planck law does reduce to the Rayleigh-Jeans law at large wavelengths where it's applicable. So that's all pretty nice. So he ends up getting exactly as far as he knew at the time, and we now know even better than he did, You get exactly the black body spectrum from this by making this totally bizarre hypothesis that energy can only be added or subtracted to the electromagnetic field in chunks with sizes that are proportional to the frequency of the radiation. That is a completely ridiculous, unheard of hypothesis. So I'll just stop there before I tell you, of course, as you already know, why it turns out not to be so ridiculous. Any questions, comments on that? Did we get Andy back? No, we haven't got Andy back.
I think he left the room. I'm keeping an eye.
He unmuted just before disappearing, and I figured he was just so excited to ask a question that he swiped the wrong way, but maybe not.
So very quickly, this the Planck constant came to be just because he wanted to fit the data. He did not have any other philosophy or any other ideas working around. The
That's
Planck
exactly
constant,
right.
which ended up being one of those most fundamental constants on such a deep level, it's just a constant to fit the observed data from black body.
That's right. I think it's really important to emphasize that he was just doing data fitting, right? I mean, not quite. It wasn't quite that bad because he wasn't just fitting the data. He wasn't doing quite what Kepler, for instance, had done. Kepler took observations and then he found that with Kepler's laws, his three laws, which he had no idea why they should apply, that they fit the data. Planck was doing something a little bit better in that he was making a hypothesis that had to do with kind of the fundamental physics that's going on. And then he followed the entailments, oh, I love that word, of that hypothesis to see that it did give him the result that he thought it might. I mean, he made it, it was an educated guess because he knew that what he needed to do was to suppress the high frequency modes. So it was certainly a reasonable hypothesis. The idea that it should be as simple as just, well, let's let the chunks be proportional to the frequency. Could have been chunks proportional to frequency squared. It could have been some more complicated function. This is kind of the simplest thing you could imagine is just to let those chunks get bigger in proportion to the frequency. And it turned out that in relatively short order, that gives you a formula that does fit the data perfectly. But it's also a good segue to the next slide, slide 6, because Planck never, well, I shouldn't say never, he did not think that that's what was really going on. He really thought he was just making an ad hoc assumption that would somehow be explained using pre-existing classical physics or something. He really didn't think that that was what was genuinely going on. So he was uncomfortable with it because it had bizarre implications for the nature of light. The idea was that somehow light itself came in chunks. And that just seemed completely at odds with everything we knew about light. But 5 years later, in 1905, Einstein used the same hypothesis to account for a completely separate phenomenon called the photoelectric effect. And he found that not only was it the same hypothesis, but it was the same constant. He could explain. So what is the photoelectric effect? The photoelectric effect is the observation that light of small enough wavelength falling on a metallic surface could result in the emission of electrons from that surface. No matter how small the intensity, even weak light, so ultraviolet light in particular, no matter how weak it is, it will generally emit electrons from a surface. But if you shine infrared light, say, or even just red light in most cases, on the same surface, no matter how bright that red light is, it doesn't emit electrons. And Einstein, and that's kind of indicated schematically over at the right there. The way they did this was to shine light on a surface, and then it's called the emitter there, and then they'd collect those electrons on a cathode that is biased with a voltage. And the important thing about that is what they could do is they could put a voltage on that upper plate that would repel electrons or they could put a voltage on that upper plate that would attract electrons. And then they could measure the amount of current, electrical current, that flows in the upper wire as a result of the electrons being collected by the cathode, and determine how many electrons they're collecting. And what they found was a graph like that at below at the bottom right, that as they increased first of all, for a repelling voltage, they never got any current because they could repel the electrons no matter what. And as they increased that voltage, they ended up getting, at some point, as they increased the voltage and collected the electrons, they got a saturation current. And so they could get that maximum current. Presumably, when they got the saturation current, they were getting the maximum possible. They were getting all of the electrons being emitted. And by playing with this, I don't want to dwell on it, so I won't spend a lot of time. But they found out that for light of a small enough frequency, they simply didn't collect any electrons. There weren't any electrons to collect for low frequencies. And then at some particular frequency, all of a sudden you start collecting electrons, and the voltage, the so-called stopping voltage, that V naught below, the voltage that you needed to apply not to collect them, started increasing, suggesting that higher and higher frequencies produced larger energy electrons. You had to apply a retarding voltage that was higher and higher to stop collecting them. And this data wasn't known the data itself was pretty dirty. But what Einstein said is, well, let's suppose that the light comes in chunks with energies proportional to the frequency, and that it takes a certain minimum amount of energy to eject an electron. Once you reach that minimum amount of energy, you start ejecting electrons, and then as you go to higher and higher frequencies, the excess energy in that chunk goes into kinetic energy of the electrons, so that the electrons come off with higher and higher amounts of energy. And it takes a higher stopping voltage to stop them. And he found that if he assumed that the chunks of energy were some constant times the frequency, that he could reproduce the observations, which were, as I say, pretty sketchy at the time. This was not the observational evidence was not very well known, because it turns out to be difficult to do this experiment well. But that was what he did, and it turned out that the proportionality constant he needed was the same one Planck needed. Planck's constant, it was the same amount of energy per chunk that Planck had used in talking about the black body effect. This is the work that Einstein got his Nobel Prize for, was the photoelectric effect, explaining the photoelectric effect using the same hypothesis ultimately that Planck had used, black body. He did not get a Nobel Prize for relativity or for Brownian motion, the other thing he explained in 1905. 1905 is often referred to as the year of miracles. Annus Mirabilis. Because of the fact that he published 3 papers that year, one of which earned him the Nobel Prize. Special relativity did not, but is largely considered pretty important. And then his explanation of Brownian motion came in the same year, and I won't talk about that here at all. But this was, this combined with Planck's work probably convinced Planck too that it was more than just an accident, and that his hypothesis must actually mean something. And to a very large extent, Einstein was responsible for making people really believe the quantum hypothesis that launched quantum mechanics, which is interesting given the fact that he was later came to blows with quantum mechanics. In terms of the uncertainty business and playing dice with the universe and all that. So let me stop there before we just finish up with the quick last slide. Any comments, questions? Oh, Benjamin, I know you'll want to talk about this after the next slide, but hold those questions until then.
Happy to wait. Good to see you all.
So let's just finish up the last slide because it just kind of gives you a where did it go from here. So Planck's hypothesis of the quantized energy levels and Einstein's use of that same hypothesis to explain the photoelectric effect really did effectively launch quantum mechanics, which took a couple of decades, more than 2 decades afterwards, to really fully come to fruition. But the important, kind of some of the more important things along the way, and I've linked to a Wikipedia article on the history of quantum mechanics that talks about these in more detail, was about 8 years later, Bohr discovering that he could explain the spectrum of hydrogen by assuming a quantized atomic obits, not obits, not dying atomic atoms, but yeah, orbits, quantized atomic orbits. And Planck's constant once again reared its ugly head in that. He found that he could explain the orbits of hydrogen as in terms of quantized energies that once again used Planck's constant. In 1922, Stern and Gerlach discovered that the spin of an electron appeared to be quantized, that charged particles seem to have quantized angular momentum leading to quantized magnetic dipole moments. In 1924, de Broglie kind of gave a new understanding of Bohr's result in terms of what are called matter waves, the idea that not only is light have these kind of chunk-like particle properties, but that matter has wave-like properties. And this was kind of the dawn of the whole wave-particle duality idea that's embedded in quantum mechanics as well. This is now 20 years after Einstein. So a lot of stuff going on in there, a lot of kind of screwing around, trying to figure out what's going on. But it wasn't long after de Broglie that Schrödinger came up with his wave equation, which was the subject of the quantum series that we finished last week after 5 episodes. Anyway, so all that's pretty interesting history, and I think the thing that's interesting to me is really the fact that at some level, the development of quantum mechanics seems like it took an awful long time. Some elements of it, given what had been understood by the time Einstein and Planck had done their work on radiation. But on the other hand, of course, it was coming to terms, really coming to grips with just a bizarre new conception of how the world works. So, okay, I think I'm done there. Let's open it up. Comments, questions, whatever. If you'd like to come up on stage, raise your hand. We'll bring you up. And yeah, go for it. Bert?
Very nice summary.
Thanks. Yeah. Hey, Andy, you're back. I don't know if you swiped. I saw you unmute and then disappear off the stage. I don't know if you had a question back then. If you did, feel free. Otherwise, I'm going to threaten you with Benjamin. Maybe we'll let Noble, Dr. TM. I don't know that we've been introduced, but why don't we let you have a shot at it first?
Peace and love to everybody. My name is Dr. T. I am self-proclaimed the professor of energy and consciousness. So I'm going to give my perspective.
Okay.
So energy is communication, not the way we think in physics. That is the inverted form. You understand is energy is the communication. Now, the communication comes from the passion of the soul, which is I am within everyone, which is the eternal real self. So when a person thinks he is a body, he's developing what I call is the iOS, illusory operating system, which creates an EMI, electromagnetic interference.
Dr. TM, I'm going I'm going to stop you. I don't mind giving you maybe another 30 seconds or a minute to kind of summarize, but I'm listening to what you're talking about, and of course, reading your profile, I can see that you have some ideas about these things, but these are not ideas that fit within the scientific paradigm, which is what we talk about in here. If you'd like to kind of push back on that for 30 seconds or a minute, I'd be happy to do that. But otherwise, we're going to kind of limit our attention to established science, which is what we do in this room.
All right, thank you so much. I'm sorry.
Okay, all right. Yeah, no, you're certainly always welcome here, but we do that. One of the nice things about limiting our attention to well-established science is I don't have to really I don't speculate. We don't go into speculative science, and at the very least. Some of these concepts get speculative. Sometimes I think most people would probably call them unscientific, but we don't even need to go there. They're speculative, and that's enough said. So let's see. Anybody else need to, if you'd like to come up on stage, do so. Benjamin, I'm sure you have something to ask, although I don't know that I said anything very controversial here.
Just
And I apologize for being late.
That's fine.
And I don't find it very controversial. I
Yeah.
do think it's fascinating that the black body effect, black body radiation, plays a kind of disordinate, like disproportional role in kicking off the conversation about quantum. I think that's fascinating.
Yeah, it is fascinating, and I don't think it had to be that way, right? I think it is, in a sense, a historical accident. The photoelectric effect probably would have been, had we had better experimental data for it, probably would have been a more obvious seminal event. So I agree with you. I think it's interesting that black body radiation was the vehicle. The hydrogen spectrum could have been the seminal event too, right?
Spectrum lines that show up when you split light. I mean, that's been a good anchor for this field of study, I think, for a long time.
Yeah. Yeah, it's a more obvious thing in a way. I mean, the spectra, the characteristic spectra of atoms was a really obvious thing pointing at something being quantized. But, it wasn't very long before this that, in fact, let's see, now I think I have to take that back. It was actually after this, at the time of the black body radiation and photoelectric effect, the best model of an atom was kind of the so-called plum pudding model, the idea that it was a little electrons in a field of negatively charged electrons in a field of positive charge. We didn't know about protons and neutrons or anything like that. And the physicists' best attempts to explain atomic spectra had to do with finding the stable equilibrium point of, say, 10 electrons in what's that? Is that a neon atom? If you have whatever atom has 10 electrons, what's the stable equilibrium positions of those electrons? And then what are the oscillation frequencies of the electrons around those stable positions? And what might those frequencies be the radiation frequencies, just because the electrons would vibrate back and forth and emit radiation of some form? That was an attempt to explain radiation that miserably failed, but it was kind of the most obvious thing before we had the so-called nuclear atom, which led in pretty short order to Bohr's ideas.
So from your final slide, de Broglie, right, murdered his name. De Broglie.
Say again?
De Broglie.
De Broglie, yeah.
De Broglie.
I think there might be an accent in there that I've missed, but sorry if I did.
I say
the
de
other three
Broglie,
are pretty.
De Broglie? Yeah.
Broglie.
something along the
The
lines
other
of those
three are
lines.
pretty well known, but de Broglie's contributions, I think, are kind of interesting because he's really setting, as I understand it, the table for Bohm's and eventually the pilot theory.
Right.
And the pilot theory is kind of a stalking horse candidate amongst all of these options. So I think de
Yeah.
Broglie is
No.
kind of more interesting, perhaps now than he was in history.
Right. I agree with you. And it's one of the things I think that really has come out of trying to understand the measurement problem in quantum mechanics, and what uh, your favorite target, the Copenhagen interpretation, which I think is a lot of people's favorite target. There's something, we're kind of going far afield here, so to speak. But de Broglie, with his, I remember when I learned all of this in university, I I always kind of thought that de Broglie's contribution seemed obvious at some level. But that was largely because notice it came 11 years. Just a couple words about it. It came 11 years after Bohr had quantized orbits, and at least for in its application to the hydrogen atom, it really amounted to nothing more than saying that the circumference of an allowed orbit in the Bohr model of the hydrogen atom was an integer number of wavelengths of the electron, using a formula that he had developed. He said, if you assume that the wavelength of a wave is its momentum, is Planck's constant divided by its momentum, then you get a wavelength, and the circumference of these Bohr orbits is just an integer number of those wavelengths. And that seemed like such an obvious thing in some ways. It's hard to imagine that it took 11 years to get to that. But it did, and I still, to this day, I don't quite understand what the barriers to getting there faster were. But and then as a result of that, largely you kind of merge it with Bohr's ideas and don't appreciate the extent to which de Broglie's ideas about quantum mechanics, about these waves and the guiding of particles with waves that led to Bohmian mechanics, how much kind of sense that makes. And I think it is true that the Copenhagen people, of course, did kind of take over the interpretation of quantum mechanics. And that's something that's getting sorted out, very slowly. So it's an
Well, I
sorry,
agree. It has been an uphill climb. And I'm only
yeah,
making progress very slowly.
yeah.
But you guys are coming along finally. I appreciate that.
Well, I'm just glad you've been there to lead us, Benjamin. That's all I want to say.
I don't take any credit that I don't deserve.
Okay, let's see. So, any other comments or questions or ideas
Completely
for next
unrelated.
week?
I want to
Say-
point out that as soon as Ben's daughter learns to drive, he's going to be wholly unemployed.
That's right. Yeah. Hey, Bert, I saw
Yeah,
you
I'm
unmute.
looking forward to that, to be honest. It's not my favourite type of employment. Although it does give me a chance to listen to audiobooks and listen to you guys and join. I'm now home, so I can now be sarcastic and contributive
Okay, good. Well, we
in
expect a lot
equal measure.
more. We do expect a lot more sarcasm than we've gotten so far. So,
Well, there's already been a very sarcastic gif, which I still slightly guilty about, but yeah, it's all good.
Bert, I saw you unmute. Did you have something?
Yeah, well, yeah, I just wanted to. I've been like taking this in a little bit and thinking about all the implications. And I missed your very beginning of your lecture, and you may have covered this already, but I just over the years have like appreciated black body curves more and more. Um,
I can
the
imagine.
That was a very well chosen sentence. But
and that if you've seen a picture of my wife, you may get that there's a joke in there. But no, there's the in astronomy, the astrophysicists that I work with, it's all about looking at the spectrums of stars, of ionized gases, of this and that, and the temperature of those items in the black body curve plays such an important part in that. Saul Perlmutter, who got the Nobel Prize for studying supernova curves, and calculating, that the universe is accelerating in this expansion. You
Hmm.
know, I continue to work with him on new projects that are, wanting to measure more and more of these supernovas. Um,
Further,
and
more distant ones, I assume, right?
well, more distant is not necessarily his goal. It's
Hmm.
more like more of them, like
Uh
getting more
huh. Just getting
statistics.
better statistics. Yeah.
Right, right. Because if you go from his original paper that he published in, what was it, 1998, studied 17 supernovas from Hubble data.
Huh. Yeah.
Yeah,
That's almost like Hubble himself, right? Hubble based his kind of conclusions on some
right,
pretty skimpy data.
right. And now since then, there's been hundreds of supernovas that have been added, but he wants to get up into the thousands, several thousands. Um, the Yeah, just black body radiation is so useful in science, and it really
Yeah.
does tell. It tells you not only the temperature, but what. Well, then you look for emission lines or absorption
Right.
lines, and that tells you what things are made of, and all the stars. I mean, this is a really big point, and in certain other rooms here on Clubhouse, we have had these conversations about stars and what they're made of and what they are, and yeah, you can tell the temperature of them. Look at the emission lines, you can see the chemical makeups. Um, Sometimes there's some redshift involved, although for stars here in the Milky Way galaxy, not so much. Yeah, so it's a very cool topic.
Yeah, and I was just thinking I should have. In fact, I wonder if I can. Let me see if I can do this. I should have put one more. Ah, there's a good version. I'm gonna just copy an image and throw it on a seventh slide here if I can. Let's see. Where are my slides? Now I can't find my slides. Oh, I've closed my own version of my talk. Let's see. Anyway, I wanted to talk about the solar spectrum. The actual solar spectrum that we receive is a really dirty version of a black body spectrum. Let me get to this and put this up here.
You're mentioning redshift in our galaxy makes me think: are your instruments sensitive enough to detect redshift of local stars within a few hundred light years, type of thing, or a few thousand light years?
Oh yeah, you can definitely see stars within the Milky Way coming towards us and receding
Cool.
due to the rotation of the overall Milky Way.
Yeah, no, I mean, in terms of their motion relative to us, is that
Yes,
are your
yes,
instruments they're sufficiently precise to measure that?
yes, yes. You can definitely see redshift within the galaxy.
Cool.
But
So
yeah,
I
those are.
just I just created an eighth slide. If you might have to refresh or something, but if you go to the link at the top now, the eighth slide is a copy of the solar spectrum. Yeah, at sea level. And you see that it's a massively degraded black body radiation. Once again, it puts most of the energy coming down is in the visible range, but there's all sorts of bands of light that are absorbed by the atmosphere. On top of that, I think it. Let's see, does it talk? I guess it doesn't. So the spectrum, I guess the gray spectrum is what we receive from the sun, which looks kind of like a black body, but it's also got absorption. It deviates from it due to absorption in the solar corona, the photosphere of the sun. The light coming to us from stars always has absorption lines from the star itself, and then even more absorption that goes on if it has to come through the atmosphere because we've been unlucky enough to be using a telescope that's not above the atmosphere, as Bert would probably say. And you end up getting lots of holes in it, but you can still see the fundamental kind of black body characteristic, and you can still kind of tell from it if you know something about how the atmosphere absorbs light. You can kind of rebuild the spectrum from that and tell that you are looking at something that is a temperature of what is the sun? Is it 6,000 Kelvin? What is that? Do you know, Bert? I think it's
Yeah, it's in
something
that
like
range.
six.
Yeah.
Yeah, right. So it is a body that emits mostly at kind of the blue end. That's why it's kind of whitish. It's not red hot. It's more white hot. But there are stars. I don't know, like what's the highest temperature? Do you know the highest temperature for stars? I would think it's probably 8,000, 9,000. I don't think it's 10.
Um, I mean, if you're not talking about neutron stars or anything, yeah,
Yeah, no, just a regular
yeah,
star. I think that
yeah.
I think these bright blue white stars I think are typically still less than 10,000
Hmm.
Kelvin.
In photography, you typically select about 5,700 as the daylight color temperature, don't you? So I don't know if that's I don't
Probably
know.
related, huh?
Yeah, well, it's very related to the surface temperature of the sun, but I don't know how modified by the atmosphere it is.
Right.
Yeah. Anyway, that's another question
Yeah.
for another day.
Yeah. At one point, we were designing a light source to illuminate satellite servicing spacecraft, and they wanted to simulate what it would look like to the cameras that had red, green, blue filters on the cameras as one satellite approaches another satellite. And so the light source that we designed had to have the solar radiance balance between the characteristics of this particular camera's red, green, and blue filters to match the solar radiance in those bands. And so the light source, kind of was tweaked, with different combinations of LEDs to get that balance, and in essence create a daytime white balance.
Right. With just a few discrete frequencies. Right?
That
Basically manipulating the human eye to make it look like it's the same as daylight.
that's right, because your eye can't distinguish between like two wavelengths that combine to give the same response as a single wavelength
Right.
um, within a given waveband.
That's one of the reasons we vaguely tolerate LED lighting. But if you look at the spectrum of a lot of LED lights, it's terribly gappy, and
Yeah.
can be one of the reasons. Yeah, I think the eye, I don't know to what extent the eye can't distinguish. I don't know what whether how true that is on a physiological basis, but because pretty sure you can tell the difference in quality between two lights that on first glance perceive the same, but one's got massive holes in the spectrum. I'd be interested to
Um,
dig into the physiology a bit more about what
right,
actually is
because
perceivable.
it is very fascinating. That's called colorimetry, right?
Yeah,
Um,
exactly.
and our eye, because our eyes have a red response, a green response, and a blue response curve. I could take a white wall and illuminate it with a single wavelength, and you would say, okay, that is, for example, orange. But then I could take away that orange light source and hit that same wall with two different wavelengths that kind of stimulate the same combination of red, green, blue, and you would
Yep.
perceive it as orange, but the orange wouldn't even be on that wall.
Yep. Yeah. Yeah.
Yeah.
Interesting. It's like the visual equivalent of how audio compression works effectively by directly noting that you've only got 11 hairs or whatever it is in your cochlea that can determine different frequency bands, and it's a superposition of those. It sounds similar with your different types of color receptors.
And I think you've run afoul a little bit of this in trying to create an indoor rainbow, right? If you try to create an indoor rainbow by shining a brilliant light through mist created in the shower or something, you run into the problem that really bright lights are typically LEDs, and you can't create rainbows. They don't have all the frequencies in them.
Yeah, exactly.
So I am with Ben here, and that is that I don't think physiologically LED light is the same as some other lights. We have a light that's an LED light. It must be a really poor quality because whenever we turn it on, we just feel really deeply disappointed.
I think they've gotten better, with I don't know exactly what they've done. I think in some maybe phosphor coatings in some cases, but
Yeah, you need to look at the color rendering index. That's if you want a light
Right.
that so look for a CRI of like 90 plus. If you really want to go nuts, go 95 plus or whatever. That'll make a huge difference because if this, I believe that's right, Bert,
Right.
right? If the CRI is high, then then you're closer to the black body, to a full spectrum, I think.
Yeah, a lot of these quote white
Yeah.
light LEDs are blue light emitters with a phosphorus coating that gets stimulated and emits a type of a black body kind of fluorescence
Right.
combination thing that kind of gives the illusion of a white light, right?
I
But
think
Yeah,
one of the
spectroscopy is the key that
yeah.
unlocks all the
I measured
secrets.
this with a spectrometer once. I bought like £1,000 spectrometer. I actually sent it back to Amazon because I wanted to use it temporarily, but I bought it for a very stupid reason. If you mind me telling a 30-second story, John,
yeah, go ahead.
this very
I
stupid
mean, no,
reason.
go ahead.
I don't care either way. I'm going to tell it unless you mute me and remove my green butthole. So you just remove me and bleach me to stop me talking. So the yeah. So my wife bought from Amazon a well-intended blue light filter for the kid's iPad, and it said this is a visible blue light filter, and it's nice and clear. And I got this thing, and I took it out the packet. I went, this is £20, like $30 to go over an iPad screen. And I looked at it. I thought, how the hell can something that's not yellow block blue light? So I was suspicious, and I should have just said, send it back. It can't block visible blue light if it's not yellow. But I didn't have the courage of my conviction, which was ridiculous. So I bought £1,000 spectrometer to check that piece of clear film didn't block blue light. I mean, and I felt like such an idiot. I felt as stupid as the day that I typed 3 times 4 into a calculator. That was the day I threw my calculator against the wall and got better at mental arithmetic. And this was the day that I sent the spectrometer back, because I'm like, how the hell did I not just insist on returning this rip-off? In the end, she used a bit of well, in the end, we did buy another one that is yellow, but it turns out that a very cheap craft film that's yellow, of course, blocks the blue light. You can't block visible blue light unless you're yellow. But while I had that spectrometer, I pointed it at a whole bunch of different lights, and I saw the massive gappiness in all the LEDs, especially back in those days, which was it's like 10 years ago. This was the early days of home LEDs, and they were terribly gappy. They might kind of look like they're white or slightly yellow, but they were just huge holes in the spectrum. Anyway, end of story.
Yeah. Yeah, I know that, and that's the early. I mean, I think it's gotten much better with LED Christmas lights, for instance, right? And some early on, well, and even now with cheap ones, there's just something kind of glaringly ugly about just cheap LED Christmas lights they don't have the warmth that an incandescent does. And the other problem, of course, I mean, especially, I guess, you guys are 50 hertz, are you, Ben? Are you 50 hertz over there? Your AC?
Sorry, buddy. I was just in the middle of recording a video, but I stopped it because
Oh,
it's okay.
oh,
No,
sorry.
it turned out the piece of wood that I was trying to split for the video wasn't going to split anyway, so I'd hit it 3
Okay, so I
times and
saved you.
and then started swearing, so it needed redoing. We are 50 hertz AC here in the UK. Yeah.
And that creates, because we have enough of a problem. There's kind of a subliminal, for LEDs, the blinking that you can easily see if you take a video of an LED lamp with your
Your phone,
iPhone,
or yeah.
right? You can see
And
that
it's
thing
much less
going in
bad
and
in
out
an
of phase.
incandescent bulb, of course, because it's got
Right.
this bad word for it, but thermal inertia. It's got
Thermal
thermal
inertia,
mass.
right? Right.
Yeah, so it doesn't cool anywhere near as quickly. And the
But that is
phosphors,
another
unfortunately, don't quite cut it. They also dim really quickly. So LEDs really do flash.
right. And so there is kind of that subliminal psychological effect, I think, that just comes from the blinking, and that subliminal thing, I think, can be kind of problematic for some people. So. Anyway, okay, well, good. I think I'm going to suggest we start winding it down, unless anybody has some burning comment or question.
I do have one. I'm not sure if you're going to cover this next time. You said you're going to extend this discussion to a next time. So I'll just throw it out there and let you decide. So we have this black body, and let's say we have this. Let's imagine like a red laser, just to make things simpler. And you're shining it on this black body, and so this black body needs to absorb whatever you shine on it by definition. So it's absorbing all that red laser, but then it's shining some other light based on the formula that we've seen. The classic interpretation or the classic definition of temperature is the jiggling of the atoms. So when the atoms are jiggling more, we consider them that they have higher temperature. My question is, how do we marry these two views together? So is it that when we shine the laser, those atoms are starting to jiggle more? And if that is the case, where are the photons coming from? When the atoms jiggle, they jiggle their electrons as well, and so when they go up and down, they start generating those other photons.
Well, that's probably the classical. That would be kind of the fundamental interpretation, I guess, of that. Ben, did you? It sounded like you were going to address the question somehow. Did you have something to say?
I don't think we need to want to go into it today, but I would just love when people start to ask what really is temperature, because it isn't well understood. And when I first learned it as the rate of increase of entropy with energy input, it's such a mind-bogglingly different way of looking at it, and of course completely compatible in most circumstances, but mind-bogglingly different way to thinking of temperature as to how we are normally told about it. And it's
Right.
the only way you can explain negative Kelvin, which still I have a lot of people who are pretty decent scientists. When I mention negative Kelvin, they're like, "You're off your head."
Yeah.
You're off
The
your
the
head.
the the problem with, I mean, and that whole thing, that's maybe something we should talk about sometime. But there is this thing that if you go to higher and higher temperatures, eventually you get to negative infinity, which is just a little hotter than positive infinity, and then it gets hotter and hotter and hotter until you get to negative 0.001 or whatever, negative zero, just the other side of zero, which is infinitely hot. And that all sounds completely ridiculous until you realize that our measuring of temperature is in some sense backwards. We should really be specifying temperatures, not as temperatures, but as kind of inverse temperatures. If you, it's similar to talking about slowness versus velocity. There's a lot of situations in
Or
which it's
cold
better
versus
to,
heat, right? People talk about the
well,
cold getting in. It's different to that, but it's the same kind of.
yeah, not so much. It's just that if you take a 1 over temperature view, then temperatures run from positive infinity to negative infinity smoothly with nothing weird going on at zero. Zero is really hot. It's when all energy levels are occupied to the same extent. Negative temperatures have more energy in upper energy levels than in lower energy, but it's a nice smooth thing. Part of the weirdness that you're referring to is the fact that we use temperature rather than 1 over temperature. Yeah. Oh,
Yeah,
to express it, we
but
should talk about coldness. That's what you were saying, right? We should talk
yeah,
about coldness rather than.
but having to resolve why you get to a negative, why you go suddenly from a very high positive temperature to a very high negative one, and understanding that from the standpoint of combinatorics, and energy states and the possible energy state, that's quite interesting. When you do reconcile it, it does come together quite nicely.
Right.
It's quite
Yeah.
easy to. It's actually quite easy to. It would make a good bite of physics. It's quite easy to understand.
Yeah, that would, and maybe we will do that. But I think maybe the better extension of this, just to answer Shamash a little more directly, if I do something next week, it'll probably be something more related to the greenhouse effect and how black body radiation, how one determines equilibrium temperature of a planet with and without an atmosphere, et cetera, because that's some nice energy transfer kinds of calculations that go on there. The Earth is heated with a pi r squared kind of capture, right? The cross-sectional area of the Earth is important for how much energy it intercepts from the sun, and then it gets warm, and then it radiates black body radiation at its temperature out over a 4 pi r squared kind of an area out in all directions. So it receives directly from the sun, radiates out in all directions, and it's figuring out what that equilibrium temperature is, and particularly the complications that result when you put an atmosphere around it,
It,
that end up
it
doing the,
also
the greenhouse effect thing.
also
Yeah.
ties into the modes of vibration you were talking about earlier, though. It's worth talking about the different types of molecules, carbon dioxide, nitrogen, whether they're linear, whether
Oh
they're
man.
what shape they are, how many different vibrational modes they have, and why that makes water and CO2 such good greenhouse gases. And Sam would be to talk to this even better,
That's right. Yeah.
and why it
No,
makes N2 less of a greenhouse gas and all these types of
that
things.
would be a better topic for either you or Sam. That's more in your wheelhouse, I would say. Yeah, but maybe we'll do that next week. We'll see. I haven't figured out yet. But I think if we do an extension of this one, that's probably the more obvious direction to go. And then I'll put the temperature thing in the hopper too. Oh, there's Sam. Speak of the devil. Hey, Sam. How are you doing?
Hi guys, good to
Good.
see you.
Yeah.
Yeah,
Uh,
if you organize that room, I have plenty to say about greenhouse gases and vibrational states and shit like that.
yeah. Yeah. You should do it yourself probably, but maybe we will.
Yeah.
Okay. Any other things? I think I'm gonna wind us down. So yeah, thanks for everybody for coming. I'm gonna play us out with my favorite tune, "Gravity," John
Wait,
Mayer.
can
Yeah.
can
Oh, go ahead,
I
Sam. Oh yeah. Oh yeah. That's right. Tell us about things coming up.
no.
No.
I don't have anything
Well,
coming up.
Shamash has to too. So go ahead, Sam.
I just maybe this is not the place for it. No, forget it. I was
Oh,
gonna read a passage. I was gonna read a passage on Zoroastrianism for Benjamin,
oh yeah. No,
but
don't do that here.
yeah, this is not the place for it. So maybe in one of Steve's rooms I can do that.
Yeah. Good. Shamash, did you want to talk about your philosophy series? You
Sure.
certainly should.
We're gonna. So this is news for some of you. Some of you already heard me advertise this. We are on YouTube. The Scientific Discourse Club is on YouTube. Finally, we have this nice YouTube channel where we are posting these weekly rooms. I'm waiting for Sam to come back so that we can post his rooms as well. Uh, we're just putting them out so that if you want to refer back to them, because Clubhouse does a very bad thing where you sometimes the replays get lost, etc. So if you want to refer back to them, or if you want to refer a friend to those lectures, you can find them as well. So some of John's lectures are being posted over there, and some of the things we're doing on Wednesday as well are being posted on that channel. I started like 2 or 3 weeks ago this philosophy dash mathematics dash logic series, where we're gonna start building up little by little or treating, let's say, the common problems in the theory of science, common problems in knowledge. Last time on Wednesday we did one on the philosophy of mathematics. So what mathematics is really about, and what are the problems that come towards it when it's applied to science. And in the future lectures, we're going to explore that connection between math and science more and more. So the name of the house is Philosophy Wednesdays. You can go there, of course. Give a follow to our founding members for more. Thank you, John.
Yeah, thanks, Shamash. And let me just really tout what Shamash is doing, because I think most of us know you can go into lots of rooms on Clubhouse and find people arguing, a form of philosophy that I think is rarely informed, not always uninformed. We have some good philosophers on Clubhouse. We don't even have Wissam here today, but he always hangs out in the chat and gives us good feedback, but we never get him up on stage. So there are people like that, and people like Shamash, who talk real philosophy, right? And do it not just to get in arguments about semantics, which is what philosophy things so often seem to be. I particularly resonate with Shamash because his form of philosophy, it veers toward the mathematics, logic, science end of things, and I think his Wednesday series is really gotten off to a great start, well attended and really fun. And of course, he's just a good guy. I also wanted to just mention, Ben, did you want to say anything about your YouTube adventures?
So, well, yesterday I redid the Slinky experiment properly using the trigger, so dropped from a little bit higher. So I'll put the link to that in the chat. But physics is about a third of what I do on my channel. It's physics, mainly physics and DIY, and they may be separated into other channels. But right now, come and join smartview.tv, and you'll get a daily short, something interesting to do with physics, one way
Good.
or another.
So
Great.
Shamash, what do I need to do to get my rooms on the YouTube channel?
You
Is
don't have to
there?
do anything, sir.
Oh,
You
okay.
just have to run the rooms again, and I will be there for
I,
you. I'm gonna do the whole
even
thing.
better. I don't have to do
I'm,
anything. That's awesome.
I'm, I'm gonna
Yeah.
record them, and I'm gonna post them, and I'm gonna edit them. You just have to run the rooms, sir.
Great, great.
Okay.
That's the best kind. Thank you.
All right. So I'm going to play us out, as I was mentioning before. Thanks for coming, everybody. And we will, I think, see you next week.